Enthalpy of formation. In the first 40 chapters of this book, the problems always concerned a fixed chemical composition and never change of composition through a chemical reaction. Therefore, in dealing with thermodynamics properties, we use table of thermodynamics properties for the given substance, and in each of these tables, the thermodynamics properties were given relative to some arbitrary base. In the steam table, for example, the internal energy of saturated liquid and 100 degrees centigrade is assumed to be 0. This procedure is quite adequate when there is no change in composition because we are concerned with the change in the properties of a given substance. The properties at the condition of reference state cancel out in the calculation. When dealing with the reference state in the section 1410, we noted that for a given substance per half component of mixture, we are free to choose a reference state condition. For example, a hypothetical ideal gas, as long as we then carry out a consistent calculation from the state and condition to the real desired state. We also noted that we are free to choose a reference state value as long as there is no subsequent inconsistency in the calculation of the change in a property because of a chemical reaction with resulting change in the amount of given substance. Note that we are to include the possibility of a chemical reaction. It will be necessary to choose these reference state values on a common and consistent basis. We will use as our reference state a temperature of 25 degrees, a pressure of 110 megapascal, and hypothetical ideal gas condition for those substances that are gases. We should consider some references for the gases reference state. Temperature 25 degrees centigrade and pressure 1/10 megapascal, and a hypothetical ideal gas condition for those substances that are gases. Consider the simple steady state combustion process shown in the picture here. This idealized reaction involves the combustion of solid carbon with gaseous oxygen, as shown here. Solid carbon plus gaseous each of which enters the control volume at reference state 25 degree and 1/10 megapascal. degrees centigrade, 1/10 megapascal. If the heat transfer could be accurately measured, it would be found to be heat transfer Q control volume as shown in the picture if measured. If the heat transfer could be accurately measured, it would be found as this quantity, the chemical reaction can be written as this relation. Carbon C plus oxygen O2 gives the CO2 carbon dioxide. Applying the first law to this process for internal and first law, steady state, Q control value plus sigma MIHI on in the molar base Ni H bar I plus for the reactant, for the product Ne H bar E plus W control value, which is 0. Which is equals to control value plus HR HP, where the summation refers specifically to all reactant or all the product. Thus, a measurement of the heat transfer would give us the difference between the enthalpy of the product and the reactant, where each is the reference state condition. HP minus HR. Suppose, however, that we assign the value of 0 to the enthalpy of all the elements at the reference state. In this case, the enthalpy of the reactions is 0, H bar I for and HI bar for O2 Q control value equals to HP, which is kilojoule on kilomole. The enthalpy of ideal gas carbon dioxide at 25 degrees centigrade and 110 megapascal pressure, with reference to this arbitrary use in which the enthalpy of element is chosen to be 0, is called the enthalpy of formation. So we can write the enthalpy of formation HF bar, enthalpy of formation for carbon at enthalpy of carbon dioxide, the enthalpy of formation for any, in this example for the carbon dioxide or for any species designated by H bar F, and for carbon dioxide it is calculated and is mole. The enthalpy of carbon dioxide, for example, in any other state relative to this base is which the enthalpy of element is 0 would be found by adding the change of enthalpy between the state, 0 state, and given state to the enthalpy of formation. That is the enthalpy at any temperature and pressure, as shown. Enthalpy of any temperature T and P, H bar T and P, and can be written as this expression: H bar T and P centigrade and pressure equals to 1/10 megapascal plus the enthalpy change megapascal to T and P, where the term delta H bar represented the difference in enthalpy between any given state and the enthalpy of ideal gas at temperature and pressure 1/10 megapascal. For convenience, we usually drop the subscript in the example that follows. The procedure that we have demonstrated for carbon dioxide can be applied to any component. Table A10 gives the value of enthalpy of formation for a number of substances Three further observations should be made in regards to enthalpy of formation. Three further observations. One, we have demonstrated the concept of enthalpy of formation. Demonstrated the concept of enthalpy. Of formation in terms of the measurement of the heat transfer in an idealized chemical reaction in which a compound is formed from the element. in which a compound is found Actually, the enthalpy of formation is usually found by the application of statistical thermodynamics. Is usually found by the application of statistical thermodynamics using observed spectroscopic data. And second, the justification of this procedure of arbitrary assigning this procedure of arbitrary assigning the value of 0 to the enthalpy of the element at (25° and 1/10 megapascal rests on the fact that in the absence of nuclear reaction, the mass of each element is conserved in a chemical reaction. No conflicts or ambiguities arise no conflicts or ambiguities arise with this choice. Of reference state and it proves to be very convenient in studying chemical reaction from a thermodynamics point of view. And the third one is in certain cases 3. An element or compound can exist in more than one state. Can exist in more than one state at (25°C) and 1/10 megapascal. For example, can be in the form of graphite or diamond. It is essential that the state to which a given value is related be clearly identified. Thus, in table A10, the enthalpy of formation of graphite is given the value of 0, and the enthalpy of each substance that contains carbon is given relative to this base. Another example is that oxygen may exist in the monoatomic or diatomic form and also as ozone. O3. The value chosen as 0 is for the form that is chemically stable at the reference state, which is the case of oxygen, is the diatomic form. Then each of the other forms must have an enthalpy of formation consistent with the chemical reaction and heat transfer for the reaction that produces from of oxygen. It will be noted that table A10 that two values are given for enthalpy of formation for water. Table A10, two values for water. One is for liquid water and other for gaseous. Liquid and gaseous. Both at the reference state of 25°C and 1/10 megapascal. It is convenient to use the hypothetical ideal gas reference in connection with the ideal gas table property change given in table A9 and to use the real liquid reference in connection with the real water property change given in the steam table. Table B1, the real liquid reference state properties are obtained from those of the hypothetical ideal gas reference by following the procedure of calculation described in section 14.10. The same procedure can be followed for other substances that have a saturation pressure less than 1/10 megapascal at the reference temperature of 25 degrees centigrade. Frequently, students are bothered by the minus sign when the enthalpy of formation is negative. For example, the enthalpy of formation of carbon dioxide is negative. This is quite evident because the heat transfer is negative during the steady flow chemical reaction, and the enthalpy of carbon dioxide must be less than the sum of enthalpy of carbon and oxygen initially, both of which are assigned the value of 0. This is analogous to the situation we would have in the steam tables if we let the enthalpy of saturated vapor be 0 at 1/10 megapascal pressure. In this case, the enthalpy of liquid would be negative, and we would simply use the negative value for the enthalpy of the liquid when solving problems. The next section is the first law analysis for reacting system.